So hi guys, in this video we're going to be covering a short application of differential calculus known as rates of change. So actually this should have been probably the first one I did, I would do for this unit, but I forgot about it, so now I'll just cover it here. It's pretty simple. It's probably like the fundamentals of differentiation themselves, but I think we've already kind of covered it, so it's going to be a short video where we just go over it. So it's called rates of change, and basically it's kind of to do with how the function is changing at a specific point. So let's take the function. Let me just draw a coordinate plane, really a rough one. Let's take x squared, which actually should be touching here. So x squared looks like this, somewhere like this, and it stretches out that way and that way. So if we want to look at, let's say, the point x is equal to 1, which is maybe here, the function would have a gradient of something like this at that point. And in abstract terms, basically the slope of this tangent tells us, in more practical terms, the rate of change. So we could use in more practical scenarios this tangent. It could tell us the rate at which something is changing. One variable is changing. So if you're looking at y is equal to x squared, all we need to do to find this rate, as we know, is use first principle, which is that with f of x, we write as f of x plus h minus f of x over h. And in this case, it would be x plus h squared minus x squared over h, which is equal to x squared plus 2xh plus h squared minus x squared over h, which is equal to 2xh plus h squared over h, which is equal to 2x plus h, where we know that with using limits that h is tending to 0. So if we substitute 0 into h here, we get 2x. And that's just differentiating the function. But as I explained in the limits video, if you haven't checked it out, check it out now. The first principle is essentially like a gradient formula, where we take 2 points very, very, very close to each other and find their gradient. And in this case, it's 2x. When we substitute our x value, which is 1 in this case, when x is equal to 1, which is 1, 1. So that becomes 2, 1, which is equal to 2. So our gradient at this point, this slope of this line is 2, which means that there is an instantaneous rate of change at 2. So what exactly do I mean by instantaneous rate? Well, it's the rate of change at that specific point. So let me give you another example. Imagine you have water being poured into a glass. Let's say it's around here. When you keep pouring in, like let's say when the height is at a specific point, what's the rate of change at, like, let's say when the height is 2 cm or something? Or another way to look at it is like a baby is maturing at what rate is its brain developing at, I don't know, 2 years. This is a very random example I've just picked out. I'll show you some more examples that will actually kind of come up in IGCSEs later on. But this is just the fundamentals, just using first principle and finding the rate of change at that specific point. It's not the general rate of change, or not like with nonlinear functions, there is a rate of change at each specific point. It keeps changing, because only in a linear function would the rate of change be the same all the way around. In a nonlinear function, well, if we looked at x squared, and we just looked at the right portion, you can see it's growing and it's increasing more and more as x increases. So like the grade's much steeper here. Oh, sorry, it's much, let me just rewrite that. It's much steeper over here than it is, let's say, over here. And that's because it's nonlinear, so it's going to have different rates of change. Okay, enough of me blabbering about this. I'll actually show an example and show how to work through it now. It shouldn't be very long. Okay, so let's just look at this one example. So we have to determine if g of z, which is equal to z minus 6 times ln z, is increasing or decreasing at the following points. First thing we have to do is differentiate the function. So g prime of z is equal to, so we can use product rule here to get ln z plus z minus 6 over z. And now we have to just substitute the values of z in. So if the differentiated function, which substituted z as 1 in, we get ln 1 plus, and then 1 minus 6 is just negative 5 over 1, which is equal to 0 minus 5, which is equal to negative 5. Of course, if we were to imagine this on the coordinate plane, negative 5 would look something like this, pretty steep and going downwards. So we can see that it's decreasing as we increase x at that specific point. At that specific point, we can see the function's decreasing. So we can say at the bottom that the answer to A is decreasing. Negative gradient means decreasing, and of course that means that positive gradient means increasing. Gradient of 0 just means that it's stationary at that point. So this kind of links to our stationary unit, which actually should have followed this unit. So sorry about that. Then we look at part 2. So we can say that g prime 5 is equal to ln 5, we're just substituting z as 5 in, plus negative 1 over 5. And if we use our calculator to evaluate this, which I'll do just now, so ln 5 minus 1 over 5 essentially, and that's equal to 1.41 approximately. And since this is a positive value, which would look something like this, not such as steep a gradient, but something like that, it's increasing at that specific point. So our answer to B is increasing. And with part C, if we substitute 20 in there, we get ln 20 plus 14 over 5, which is definitely going to be, sorry, not 14 over 5, 14 over 20. Which in this case is definitely going to be positive because ln 20 we know is positive, and 14 over 20 is also positive. So we don't even need to see the specific value actually in this case. In this case, we can just say it's increasing because the question is asking if it's increasing or decreasing. So we don't need to get into the specifics of it. If we didn't want to put it in, we could put it into our calculator, which would give us 3.6957 and so on. But we don't actually need to do that. So there are our answers to this question. As you can see, it's very easy, and it's kind of what we already covered, but I just wanted to make sure that I said it explicitly so that you kind of could take that knowledge into the exam. Thanks for watching this video, and see you in the next one.